All right. Hello, this is going to be the third set of lectures that I'm recording. This one is covering chapter 3.3. Again, we're still in chapter 3, so we're still talking about algebraic functions. This video lecture is not really going to be covering exactly what the notes do. So the notes I've already posted. These I will post probably later today, Saturday. And the main point for these video lectures is to go over the synthetic division, or the polynomial division that's required to do the homework this week, as well as the rational root test. So first, let's just sort of go over how we go about finding zeros. So if we have a linear term, or a linear function, like f of x equals x minus 9, just some linear function, and again, so just FYI, when I say linear, it's the same as saying degree 1. So if we remember what degree means from a couple lectures ago, degree is the highest x exponent. So here we have sort of nothing in the x exponent, which is the same as having a 1 there. So this is a linear term because it's degree 1. We can also say that if we want to find where this is equal to 0, this is going to be very easy to do, because we simply add 9 to both sides and we get that x equals 9. So when we do f of 9, we should get 0. So finding the zeros of a linear term are super easy. Wherever possible, we are going to try to reduce higher degree polynomials down into linear polynomials. So I'm not really going to say much more about linear stuff just because it's pretty much trivial. Instead, what if we had something like a quadratic, right? So my 2 kind of looks squiggly, but this is x squared plus 5x minus 10. And so this is a quadratic, which just as linear means degree 1, quadratic means degree 2. So our highest x exponent is a 2. We do have an x to the first, but it's not the highest one. The highest one is x squared. So this quadratic one, we have a number of things that we can try in order to solve for the zeros of this. Depending on what its structure is, we may be able to find the zeros quite easily. Like, for example, if we had x squared minus 1 equals 0, this we don't really have to break out any big guns to figure out. We simply solve for x. This gives us x squared is equal to 1, and then x is equal to the positive and negative square root of 1, which of course is just positive and negative 1. So if we have a quadratic where it doesn't have an x term, like we see here, it's just x squared and then a constant term, if we don't have the middle x term, these can be quite easy to solve because they're essentially linear terms just with a square root in them. However, if we are given something like this guy, which does have both an x squared and an x term, there's no easy way to solve for x or isolate the x all on one side. So instead, we have a number of different things we can try. I know that if I have x plus a, that's an a, not a 9, and x plus b, and we multiply them out, then I'm going to get x squared plus a plus b x plus ab. And you can check that yourself, just FOIL it out in group-like terms. If I want to say that x squared plus 5x minus 10 is the same as x plus a times x plus b for some numbers a and b, then they have to satisfy this relationship. So a plus b has to equal 5 because this coefficient is this coefficient, and ab has to equal negative 10 because this value is that value. So to solve this equation, by factoring it, which is what this process is, we have to come up with numbers a and b such that this is true. Again, there are going to be a number of ways that you could attempt this. The way I'm going to show is, I think it's called the AC method. I'm not sure though. Basically, we want to find the factors of negative 10 because those will give us all of our possible a and b's. And then we want to check if the sum of those factors is 5. So we can do that here by looking at factors of negative 10 and then their sum. So negative 10 is going to be divisible by, well, 1 and itself, which also means negative 1 and positive 10. It's also divisible by 2, which will give us 2 and negative 5. And then, of course, we can just swap the negative signs to get negative 2 and 5. And is there anything else? Well, no. 10 is only factorable by 2 and 5, 1 and 10. And here we have all of the possible ways to do that. So, if it's possible to find whole numbers a and b that satisfy this, then hopefully one of these pairs, their sum is going to be 5, because these are our only possible candidates for a and b. So we do this. What's the sum? Negative 9. What's the sum? 9. What's the sum here? Negative 3 and 3. Since we find none of these give us a sum of 5, then none of these are going to work. We are not going to be able to find whole numbers a and b such that a plus b equals 5 and a times b equals negative 10, which means we cannot factor this quadratic into two linear terms with whole number a and b. So from here we could go on to a number of different things. For quadratics, there's lots of ways to solve these. The next way would be to complete the square, which we did a couple of sections ago. This is again where we're going to say, let's assume that this is equal to x plus a squared. Well, it's not, but if we pretend it is, then we can get something pretty close. So if we do this out, we just actually FOIL this. This is the same as x plus a times x plus a. And when we FOIL this out, we get x squared plus 2ax plus a squared. And what this tells us is that since we have x squared and 5x, and we have x squared and some coefficient on x, this tells us that 2a has to be 5. And again, that's an a, not a 9. Which then gives us that a has to be 5 halves. So we can then use this to then figure out what we have to add and subtract from the original function in order to make this collapsing into a square term true. So if we remember completing the square, we find some number that we can both add and subtract, thus not changing the function, but which allows us to regroup things into a simplified form. So we find that our a term is 5 halves, and then this term, which is the one that we have to add and subtract, is a squared. So a squared is 5 halves squared, which is 25 over 16. So if we add and subtract 25 over 16 from this function, we will be able to rearrange things as follows. We do x squared plus 5x plus 25 over 16 minus 25 over 16 minus 10. So we have exactly the same function here because I've simply added 0. But I can group these things together, and I know that this is going to be x plus 5 halves squared because of what we just did with the algebra. Then we just combine these things together, so 10 is going to be the same, or like 10 over something over 16 to equal 10 is just going to have to multiply by 16. So this is going to be negative 160 over, no, 160 over 16. And so we can combine these two together and we get a total of negative 185 over 16. And unfortunately, using the completing the square, this is as far as we can get it. However, if we now set this equal to 0, we should be able to find different things because we still have effectively one x in it. So we have taken these two x's, one squared and one linear, and we've rearranged things until we have just one x, and so we could simplify from here to solve for the zeros. Instead, I'm going to go on to sort of the big hitter method, which is the quadratic equation. So, quadratic equation, if you're like me and you found it easier to just memorize, is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And my a's always look like 9s, but that's an a, not a 9. And this, of course, corresponds to the coefficient here is A, the coefficient here is B, and the coefficient here is C. And we can see that since there is sort of nothing in front of the x squared, that means that the coefficient is 1. Since there's a plus 5 in front of the x, that means that B is 5, and the constant term is negative 10, so C is negative 10. We can then take all these and plug them in to solve this. So if we plug in into the quadratic formula A, B, and C as they're found in this quadratic, we would get negative B, so negative 5, plus or minus the square root of B squared, which is 25, minus 4 times 1 times negative 10, because 1 is A and negative 10 is C, all over 2 times A, which is 1, so it's just 2. We can then simplify this a little bit to say this is negative 5 plus or minus the square root of, well, we have 4 times 1, so 4 times negative 10, which is negative 40, and then we have 25 minus negative 40, so it's actually going to wind up being addition. So we have 25 plus 40, or 65, and all of this all over 2. And 65 is not, yeah, that's 5 times 13, so there's no squares in that, so there's no way to simplify this radical. So these are just the answers. By using the big gun of the quadratic equation, we are able to reduce absolutely any quadratic down into linear terms because these are going to be the zeros. So then we can say that this whole f of x equals x plus negative 5 plus the square root of 65 all over 2 times x plus negative 5 minus the square root of 65 all over 2. And that looks a little messy, but this is just the positive version of this, and this is the negative version of this. And so those give us our two zeros, and so we can factor this quadratic into these two linear terms, which then give us the zeros if we decided to go that route. Technically, these are just the zeros, so we don't really have to bother. But this is a way to factor a quadratic into linear terms. Now, the quadratic equation is super nice, and it's super powerful because most of the mathematics that we're going to encounter in the real world rarely go above degree 2. Sometimes you'll get a cubic, sometimes you'll get a quartic, but most of the time it's going to be linears and quadratics, and so we can use the quadratic formula to solve anything. However, it does have a huge downside, which is that it only works on degree 2 polynomials, that is, quadratics. You cannot use the quadratic formula on cubic polynomials or anything above it. Technically, you can't even use it on linear terms. Instead, when we go to find the roots of a higher polynomial, we have to do some clever things. So, for right now, in order to do the synthetic division, we basically have to guess around. We have to check x values to see if any of them give us a 0, and then I'll show you what we can do after that. So let's just come up with a function. Let's keep it fairly simple, and let's keep it to cubic functions. So let's say this is x cubed minus 2x squared plus x minus 2. Again, I just pooped that out of nowhere. It's just a random cubic polynomial. And now, let's try testing various x values to see if we can stumble upon a 0. Actually, I haven't tried this one yet, so this is true for me too. So let's try some obvious numbers, like what happens if we plug in a 1? Well, if we plug in a 1, then all of the x's turn into 1s, and we get 1 minus 2 plus 1 minus 2. This is going to be, what is that? Negative 2. So since that's not a 0, we know 1 is not one of the roots of this polynomial. Let's try a different one then. How about 0? Well, if we plug in 0, we're going to get negative 2. I don't even have to do any math, simply because all of these are zeros, and so they all go away, and the only thing we're left with is the constant term, which is negative 2. So 0 is also not going to be a root. Let's try negative 1. If we do negative 1, then since this is cubed and it's an odd power, this is going to remain negative 1. Negative 1 squared, though, is positive 1, so this is negative 2 minus 1 minus 2. I can already tell that this is not going to be a 0 simply because these are all negative, so they're going to sum to some even more negative number and not 0. I actually don't know what the zeros of this are, so let's try a slightly different one for which maybe we do know what the zeros are. So let's try x cubed plus x squared plus x plus 1. Because then when we do f of negative 1, this is going to be negative 1 plus 1 minus 1 plus 1. And so we see that all of these cancel, and so we get 0. Now I chose this polynomial specifically because I knew it had a 0 at negative 1. The one we started with earlier, I would have to continue hunting around for, which is very inefficient for a video lecture like this, especially since I'm not trying to demonstrate my ability at doing this. Instead, now that we have a polynomial and we have found a 0 of the polynomial, we know when x equals negative 1, then f of x equals 0. Now we get to something called the division algorithm, or the, what was it called? The division theorem? Something in 3.3, it's in the notes. This says that anytime you have a root of the polynomial, then if you take the polynomial and you divide by the linear term featuring that 0, so this would be x plus 1, so that the 0 is at negative 1. If you divide these, then you're going to get a clean division, right? We're not going to have some kind of weird remainder. However, this is kind of mysterious for people seeing it the first time. How exactly do you divide polynomials? I know how to do long division for number division, but how do we do this for polynomials? It turns out it's almost exactly the same process. We have to look at